Okay, so welcome to our systems engineering course. Today we're going to cover chapter 1 on system science and engineering, and we'll see what that entails. Just the preliminary set of definitions to frame the course and go on to the next set of chapters. I think that when I went to the syllabus, I told you why I'm here, the genesis of the course. So in the context of the presentation, this slide is not absolutely relevant. I also, going back to when the course was an elective, I used to ask people why they were there, what their interests were. But since now it's a requirement, this question has lost its luster, because I know why you're here, so you have to take the course. Most of you will tell me that anyway, so why bother asking? But what is interesting to get some feedback from you, since I told you what the course is about, so about the art, if you will, and science of systems engineering, how to do preliminarily all the right things so then we can do all the things right. I use the phrase measure twice and cut once a lot, and hopefully I gave you a good overview of what the course was about. So a relevant question is, what do you think? Perhaps what did you think the course was about? What are your thoughts about this type of stuff, let's say? Anybody wants to comment or say something? Yes.
My initial conception is that it's kind of like conceptualizing and planning the overall project, because like you can have a great idea, but you don't have a plan for it, and you don't continue to plan for it as you move through the project, and you don't have a project.
So conceptualize, that's a key word. We're going to be using that a lot. Anybody else? No? All right. So the other thing that we need to discuss is that this course is about systems made by people. They are synthetic systems, systems that don't exist. You are creating this system. There are, and we are surrounded by many types of systems that exist as part of the natural world. They are there. Those are not the systems that we're going to be targeting in this course. We are talking about human-made systems. And that relates a lot to a fundamental difference between science and engineering. So scientists, they observe and learn and try to understand and describe the natural world. They see what is there, they form hypotheses, and through the scientific method, they try to model, explain what is already there. Now, for engineering, at least I like to think so, the bar is a lot higher because there is nothing there. And not only there is nothing there, but normally you have to be better than what we call the state of the art. There is nothing there of what you're going to do, but if you're going to do it, you have to advance. Normally, to be competitive, you have to advance the state of the art. So what that means is that it has to be better in some respect, because if it's not, then you're just copying something. It's not that that much challenging, at least from the perspective in this course. So you have to be better in some respect. Maybe it has to be lower cost. Maybe it has to be smaller. Maybe it has to be faster. So some type of performance metric has to be better. So that's another type of bar. Sometimes it's not just good enough to do it in a different way, but it has to be different with the aim of making it better in some respect. So that, from an engineering perspective, sets the bar quite high for complex systems, and we want in this course to learn a set of approaches and practices to make sure that our projects are done on budget, on time, and that we meet the right features for the product. So conceptualization is a tool. It's an intellectual tool that we're going to be using, and within that we're going to be talking about things like hierarchy, dichotomy, how we, as a way of understanding and putting our hands around, if you will, complex problems, because you cannot worry about everything at the same time. You have to partition things to be able to manage them and execute them successfully. So obviously, and as I alluded to before, as things become more complex, you need to have in place a set of practices that doesn't rely on a specific people, on what, tribal knowledge, what some people believe or think or know. You have to have an infrastructure. You have to have a developmental, intellectual infrastructure that is robust, so that as a system itself, you put the input of, let's just say, an idea, and through this complex product development and execution infrastructure, out comes a product. Now, a product that meets some realistic constraints, and a big part of senior project, and you're going to learn about this, are realistic constraints versus technical constraints. And I can tell you that it's very easy to come up with just one of something. That first prototype, that actually relatively could be easy. And it can meet some technical constraints, some size, some power, some performance. But realistic constraints goes a few steps beyond that, and we're going to talk about things like reliability. Not just making one, but how do you make 1,000 and make sure that all 1,000 work, and they work for a long time and they don't break? That's a whole different thing. That's a whole different set of constraints. Manufacturability. You can make one prototype, but then when you're going to make that 1,000, you may find out that it's very hard, that it's not cost effective to make them. So that's a realistic constraint. And there are others that in a complex socio-political environment you may have to worry about. Things like safety, sustainability, regulatory compliance, and a slew of other things. So systems engineering worries about, at the onset, about all of that, and tries to partition and manage in a conceptual manner all the activities that you have to do, so when you do have a product, you comply with not just the technical constraints, but the realistic constraints, things like, can it be maintained? Can it be repaired? And we're going to be talking in chapter 2 about the product life cycle. And the product life cycle does not end with having a prototype. The product life cycle takes a holistic view of the product from the initiation, when you are developing that concept, all the way to obsolescence and retirement. it may be that for some products, the part of making the product obsolete gracefully, or updating it, or retiring it, is a big part of what you have to take into consideration as you design the product. You may have to put hooks and features in the product to make that obsolescence amenable and graceful, or make that retirement safe. So for example, ordnance design. A big part of ordnance design is how do we retire it? How do we basically put it away? Because we do hope to put it away. That's not something that you hope to use. So a big part of that design is, at some point we're going to have to retire this dangerous thing. So what are the things that we have to design into the product today to make that part of its life cycle robust? So all the way from concept to obsolescence or retirement. That's the life cycle that we're going to be looking at. So these are the things that you will learn in this course. So chapter 1, these few slides, these are the introduction to the course, to the systems way of thinking. And we're going to really dive deep in chapter 2 into this process, this general process and the concept of the life cycle in chapter 2, which is called Bringing Systems into Being. Then we're going to have 3 chapters, which are sort of, from a lecture perspective, is sort of the meat of the course, where we're going to look at 3 stages of design, but still at the system level frame of reference. And these are sequential with some overlap. So the first one is conceptual system design. We're going to, in chapter 3, look at all the activities, all the things that we have to put in place and do if we want to have a robust conceptual system design endeavor. Then we're going to look at preliminary system design in chapter 4, and then detailed system design in chapter 5. Know that all of this is at the system level, but they have different sets of activities that we do in each of those phases. Then in chapter 6, we're going to talk about system test, evaluation, and validation. So again, getting something done that mostly works, that actually is a much lower bar than having a robust design. But then how do you know if you have a robust design? We're going to discuss that in system test, evaluation, and validation, which are not the same thing. And even though we're going to go through all the details in that chapter, as a precursor of that, I'll tell you that testing is, did we design it to do what, in an isolated environment, what it's supposed to do, or was it manufactured correctly? If you get that far, that would be manufacturing testing. Evaluation has to do with how do you prove those realistic constraints. For example, reliability testing. You can have something that does what it's supposed to do, and the test will pass, and you manufacture it, and you run it through your manufacturing test, and the test will pass. But there is a different set of tests that can be done for things like reliability, or quality evaluation, or maintainability assessment. So these are the type of evaluation that you can more broadly do for a system. And then you have validation. That is the one that tells you that you really have something that was done correctly. Validation is putting the system in its intended environment of operation, what is it is going to be fulfilling its mission, and making sure that it performs, it functions, and it complies with all the requirements, both at time zero and through time, completely. That's the ultimate, what ultimately tells you that you have a viable, well-designed system. And we will talk about the different types of approaches that we can take to do that in the context of the system itself, but also in the infrastructure that we need to have, and the discipline that we need to have, and the practices that we need to put in place to make this sustainable, meaning that it happens for every project, that is not something that sometimes it gets done depending, on the people that are there, or maybe in some other team it doesn't happen because there is not a coherent infrastructure to facilitate. Because you want it to happen, it's a discipline, so you have to go through it, but you want it to be coherent so that it's not hard, that it's not haphazard. So some of these things are interrelated, and what we're going to try to do is trying to get you to start thinking at a system level, and appreciate this philosophy of stepping back, thinking about things, and making the right things so you can make things right. And that word evangelism there, it's not a religious thing, but in technology we use that word to mean that we want to convince people that something is good that may not come naturally, because all these activities will feel like a burden. It will feel like a burden because it's a lot of things that you have to do up front, and it goes against the grain of human nature in the sense that our nature is pre-wired for instant gratification, and the sooner we get some feedback, the better we feel, because we don't like to deal with uncertainty. So delaying that feedback is against human nature. So we have to look at it as an investment. An investment, and every investment requires some type of, delayed gratification, if you will, okay? If you put your money away, you're not using it, but it's growing, and then you have more. That's investing. Well, you don't start thinking and doing things right away. You think about, you plan it, you do all the things that we're going to be talking about, and you delay that gratification of just doing things. And that is against our human nature, mainly in a discipline that is male dominated, because that's also another difference. There have been experiments that they give boys a bunch of parts, and they just go at it, and the instructions are right there. They don't even look at it. They don't even talk to each other. They just start trying to put things together, see if they fit. And they give the same thing to girls, and girls, at least they look at the instructions, they talk a little bit among themselves. So in a male-dominated profession like engineering, is a miracle that anything happens, okay? But so we have to force ourselves to delay that gratification and do the right things up front to do things right later. That's what we're going to be talking about in the course. Through it, there is going to be a lot of terminology. Systems engineering is a serious discipline in itself. It has its own equivalent of IEEE for electrical and computer. It's not even part of it, even though there is a nexus between these two societies, but systems engineering has its own thing. It's called INCOSE, and that's the equivalent of IEEE for systems engineering. It's an important discipline. What is changing is how pervasive these practices are becoming through other industries that classically were not using these techniques. Because as I mentioned, this is something that came from the aerospace industry. So now, I ask again, if somebody would like to comment, what did you think you were going to learn? And this is an easier question because everybody thought something. So you know, I'm hoping that at least a couple of people chime in and say, what would anybody care to share what they thought they were going to learn? Yeah, kind of like.
I think what I was thinking we were going to learn is more about like an actual system itself, but also we're learning more about how to even produce all the requirements to produce an actual efficient working system.
Yes. Back.
Really going down the design process, like step by step, and then pulling out everything you do. Start from scratch.
Very nice. If you recall, I think that in 142, I was involved with that a number of years ago, and I don't know if they still do it, but I think they may still touch upon the design process and perhaps the waterfall model and things like that. So that's just kind of a peek into it, just to at least assert that in engineering there is a process. There is a process. But in here, we're really going to dive deeply into this process and not only go through the process and talk about it, but give you tools, conceptual tools. Now, what are these tools besides CAD tools where they have tried to put it into a program that they can sell and people use? But a lot of these tools are simpler than that. These are flows, flowcharts, checklists. They are outlines. So these are conceptual aids that you can utilize and adapt to your own project. So they are general in nature, and the challenge for you, and also the interesting part, is not how to reinvent the methodology or the techniques, but how to adapt these techniques to your very own project. And recognize that not everything there is going to be applicable. We recognize that up front. Not everything is going to be applicable. You just have to take, and that's where that technical maturity comes in that I mentioned at the beginning. You have to go through these aids, and as you adapt it to your own project, discern what you keep and what is not applicable. That's a big part of what hopefully you'll get to practice in this course through the projects. Okay? All right, so let's actually start with a formal definition of a system. And I'll let you read that for a second. Okay, so in this course, we have a formal definition of a system, and the definition of a system is not unique. There are actually quite a few out there, but this is the one that we use in this course. So I'm going to read that, And I'm going to say that a system is a set of interrelated components working together towards some common objective or purpose. This one is pretty comprehensive and at the same time succinct. So what are the things to recognize? A system is a set. So it's not a monolithic single piece of something. It's a set of components. And we're going to see that depending on the complexity, systems can be made of other systems. And as you traverse the hierarchy, at some point, you get to what we call a component. And we have a definition for that. If you get to the point of a leaf component, then you know that your hierarchy has stopped. So it's a set of components, but these components are interrelated. It's not just throw a bunch of things that are not related together and that's a system. That's not a system. In this course, for a system to be a system, the components that are part of it have to be interrelated. More data on that later. And as they are interrelated, they are working together for some common objective or purpose, which we're going to call the overarching mission of the system, from which we are later going to extract functional requirements. Now there are other characteristics of a system, and those are that the properties and behavior of each component has an effect on the properties and behavior of the set. What that means is that each component is bringing something unique to the system so that the system can achieve that functional mission. And also, the properties and behavior of each component depends on the properties and behavior of at least one other component. So that is the interrelation part. There exist interrelational links between at least two components. Or said another way, each component has an interrelational link with at least one other component. And as I was mentioning, you can break down subsets of components as you traverse the hierarchy of the system that has these characteristics. And when you get down to a point where an entity does not satisfy the characteristics of a system, that's when you know that you have a component. So if you look at it from the bottoms up, you can have components, and if they meet the characteristics of a system, that is a system now. But that system can be part of a larger system, and we'll call that a subsystem. And you can go up the hierarchy. But going from the top down, from the system down to the component, at some point you're going to reach an entity that doesn't meet the requirements that we are discussing here, as called by the definition of a system, and that, in other words, the definition of a component is that it is not a system. Does that make sense? So you have to make that test, that intellectual test, or conceptual test. And systems are all around us. I mean, really, the level of complexity of the world these days is easy to find examples of it, and you'll be questioned about that in your homework, so I'm not going to go into that. But I'm sure that you can think of many examples. Now, the components as one element of a system, we are going to, because eventually, once you have your system designed, well, guess what? Someone or yourself, well, the components have to be designed as well. And the nice thing about system design is that when you partition this system all the way to its component levels, you can very clearly delineate for these components what are the inputs, what are the outputs, and what are the processes in this component that transform those inputs into outputs. Just that, just having that clarity makes a world of difference in the way that you go about designing complex systems. Because you know for each component very clearly what the inputs are, what the outputs are, and what needs to happen in between. And if you specify inputs and output relationships very clearly, guess what? Now it's very easy to partition that design so someone is working on a component X, someone is working on component B, someone is putting those together as they emerge, so you can actually parallelize the work, which gets into the efficiencies of the actual execution of the design of the product, and you already start, so the process already starts paying dividends. Because you took some time, but later you can expedite things. That's just an example. Then we also are going to be able to articulate attributes, which are the properties, these are definitions, the properties of the components, and relationships, not only between the components, as you try to articulate what the inputs and the outputs are and the processes, but also the links between the components itself and its attributes. So by the way, at any time, please stop me if you have any questions. You want to wait for the end, that's fine. But at any time, you can stop me and if you have a question. Okay? Are there any questions? Now let's take a closer look at relationships, because we have different types. First, we have first order relationships. And these very clearly are the ones that are functionally necessary between the components, or the components on its attributes. So these are like first order relationship, they must be there. It's almost like go, no go, does it do it or not? Does it work or not? Then you have second order complementary, and they add to the system performance. They can be performance enhancing or performance based. They can also be synergistic, but they could be, so the best way to think about it is, it's not does it do it or not, but how well does it do it? And they are second order because sometimes there is some flexibility in that. So you can actually, for example, if you are designing a chip and it works, so digitally, all the ones and zeros behave as they should, but does it run at 1 gigahertz or 2 gigahertz? Well, that's a secondary, because that doesn't mean, if it doesn't run at 2, all of them, well, that doesn't mean that you have a failure in your hands. Some of them will run at 2, so you could actually segregate the ones that run at 2, sell those, and then the ones that run at 1 or 1.5 gigahertz, you could sell still at a lower price, because there may be a market for those chips that don't require the 2 gigahertz. So you can see that those second order relationships, there is some latitude, and that's what we call them second order. Then third, there are redundant relationships, and mainly those deal with duplicate components that are present for the purpose of assuring continuation of the system function. So to enhance the reliability, we will talk about how there are mathematical limits that you can compute the reliability of a system based on the components and based on the inherent reliability of the components themselves. So you can never have, for example, higher reliability of a system cannot be higher than the reliability of the component that is necessary for the system and that has the lowest reliability possible. So in other words, if you have a number of components and as a figure of merit, you have a component that is a must-have in the system, and the reliability of that component is 0.9, and everything else has a higher reliability, even 100%. But you have something that is a must-have in the system that the reliability is 0.9, the reliability of the overall system will not be higher than that 0.9. So that's something that we'll talk about. And then if you cannot do anything about that 0.9 for that component, maybe you put a secondary there, and that will raise the reliability of the system, because now you have 2. So those are redundant relationships, and that's why it's important to understand all the requirements, not just the functional requirements and the performance requirements, but also all the requirements through the life cycle, so you can do things at the design stage, like perhaps considering redundancy to achieve all the goals of the life cycle of the product. So to do this, we're going to be utilizing right away almost conceptualization tools like abstraction, which helps us deal with complexity. You should be from 451, ELC 451. That is a tool that gets used in that course a lot, because abstraction is, what it means is, or abstracting means hiding the low levels of details that are not necessary to get our point across, to manage the problem the way that we, or at the level that we want to manage or need to manage it at this moment, as we're going through these phases of system design. We're also going to be talking about implementation, which are kind of the other side. At some point it needs to be implemented, but if you have a clear specification, that becomes much more manageable to deal with the details underlying a specific component or abstraction, and very important, the interfaces. if we design at a level of interface and interoperability, and if you have clear, well-defined interfaces, and then if you have well-articulated processes between those interfaces, then from an abstraction perspective, you can give someone the freedom to go and do what he needs, this box, this component needs to do what it needs to do, however you want, as long as it meets the constraints. Functional, performance, cost, and so on. But now you have abstracted things and people can go and you can partition the work and they can do it in parallel. You can have two components that interface to each other being designed in parallel because you have this clear interface. There is an agreement that the way that this box communicates with the external world is through this interface. And that's very important. That's standards come to facilitate that agreement, as we'll talk about later. And we also will be talking about or utilizing the tool of hierarchy to be able to partition systems and subsystems. We also need to talk about the classification of systems. At the beginning, I said that we are dealing with human-made systems in this course. So that's a classification. Natural systems, which are all around us, ecosystems, weather systems, and so on. Social systems, and human-made systems. I guess I should say anthropological systems, because social systems also could be human-made, but you get the idea. We're going to be talking about technical synthetic systems, okay? Now, systems still being technical and human-made and synthetic, they can be physical or conceptual. So physical is pretty easy to understand. It's something that you see. It's a gadget, complex system gadget, right? But it can be a concept, a conceptual system. For example, a payment system that eventually may be made out of other systems. Some are software, some are hardware, but the concept itself of how transactions get routed, what type of devices get used, what type of authentication gets used, what type of security and protection, all that for a payment system or a payment infrastructure, that is a conceptual system. So it's not a monolithic, or it's not a box. So we're going to be talking about physical systems and conceptual systems as well. Another classification of systems is static systems versus dynamic. Now, dynamic refers to is the system changing through its life cycle. And if it is, that's another challenge, because you have to deal with that and manage it. But we'll say that all systems are changing in reality, but we can call systems static, and most of the systems that we're going to be dealing with are in that category of static systems. We can call systems static if it's static enough through the life cycle of the system. Meaning that whatever changes are taking place, it really doesn't take us out of the zone of functionality and performance. So we still will call that a static system. And then we have closed versus open systems. And this is very similar in the sense that all systems are open. Nothing exists in a vacuum, but if the functionality and the performance of the system is isolated and independent enough of its environment, we can say, and throughout the life cycle of the system, we can say that it is a closed system. But if the functionality and the performance of the system relies heavily and interacts heavily with its surrounding environment, then we say that we have an open system. And you'll be asked for examples in the homework. So again, this is where we're heading. We're going to be learning about tools for system design and architecting. So that's the CAD part of the course. Chapter 2 is bringing systems into being. The 3 phases of system level design: conceptual, preliminary, and detail. And finally, chapter 6, system test evaluation and validation. We talked about the difference previously. That's where we're going. So this is chapter 1. And remember, read the book, do the homework, ask questions, and don't procrastinate with any assignments. I'm going to be assigning chapter 1 homework later on today through Canvas. That's going to be due in 2 weeks. I think the most important thing is ask questions. So one of the things that I have seen is that students, you need to practice and get better at asking questions. Actually, asking questions is not as simple as you may think. The answer that you get is almost directly proportional to the quality of the question that you pose. So you have to practice at asking good questions. So engage with that. Ask me good questions. I'll give you amazing answers. Okay? So that's it for today. And I'll see you next week. Thanks.